Thank you very much for inviting me to this roundtable. I thank also previous presentations for very interesting insights. With my presentation, we'll be moving to the semantic music generation. So previously we've been talking about the generation of audio, the application of analysis of audio, etc. Here we'll be talking a little bit something a little more different, right? But it's still the music generation. So what is the semantic music generation? Actually, semantic music generation, it's everything. It's everything that is not sound. So for the semantic music, the valid semantic music input types can include not only MIDI, but the analytical representation, the graphical representation of the score. So here, for example, we have the score, the analytical representation of chords, and guitar tabs that present those chords. And the guitar tabs are also the valid input for semantic music generation. Or for example, we can have graphical representation, right? So here we have the system of graphs and or for example, the encoding that I will be showing just in a minute. So these are all valid representations. So these are not audio, right? So everything which is not audio is a valid input type for semantic music. So now we'll be talking about the music generation, well, in previous presentation with MusicML, which is audio-based model, but we've been seeing the possibilities of conditioning the output with our input, right? The input that used in MusicML is actually from another modality, so it's text. But we can conditional our generation with other parameters which are inherently musical. We have basically three groups of conditional generation. So the conditional generation itself that take the one element as input and generate another element. So for example, I give one chord to the model and it generates me the entire progression. The model has liberty in choosing the other chords, right? But the first is my input. So I'm conditioning and saying that I want to start my generation with that particular chord, for example. In controllable generation, we change the input features to manipulate different aspects of generation, or it's also frequently used during the inference with a sampling method that I will be showing just in a minute. And with constraint generation, we use the template-based approach to influence the shape of the output result. For example, I give the model a melody and I ask the model to generate a bass, right? So the melody is not free, as for example, in conditional generation, to generate whatever it wants after my input. It's very bind to that template that I given, which can be melody, rhythm, harmony, or whatever you choose to input to the model. The control can be described in terms of the stage of the constraints intervention. So we can introduce that constraints on the training stage via the cost functions, or on the decoding stage. Again, the sampling method that I will will show in the next slide. And the degree of the set of parameters that we use decides for whether this control is soft or hard. Another type of constraints that we can introduce, it's through the lyrics, melody, bass, and harmony, so, and even emotion. So the sampling method I was talking about include three main sampling methods. So as I told, via the sampling method, that's we can produce a controllable generation, and with the prediction that outputted the model. So model actually outputs the probabilities, the numerical values, and we can do all sort of mathematical things with that. So we can sort it, we can multiply by certain numbers to augment or to decrease the probabilities that were sorted by the model. So the first sampling method is a temperature. So temperature sampling. The term temperature is inspired by statistical thermodynamics. So the model the model predicates are compared to the energy, and with lower temperature comes greater stability of the decoded output. Sorry. For example, if I want the model to be very straight with the, for example, when I'm generating the bus to the melody, if I want to this bus to be, I don't know, fundamentals, for example, I will give very low temperature, or I say I don't. But the problem of that is that the model can be repeating itself, so there will be maybe not very much interesting material in the end. And if I, so in that case, I can augment the temperature, so give the higher path through, and here I can receive more interesting results. But if the temperature is too high, we can run into the hallucination that was already discussed today in the context of the text generations. Another type of sampling is keystop sampling. So with the keystop sampling is achieved by sorting the model outputs by probability, so from lower to higher, right, and setting everything below kth token to the 0. That improves the quality of by removing the tail and reducing the likelihood of going off topic. So basically, I'm telling the model I want the top 10 probabilities for that particular token or chord or melody tone. Another type of probability which is close to keystop is p-top sampling, but the computing is made by cumulative distribution, and the cutting of the tail as soon as the cumulative distribution exceeded the p-top value. So we're not telling I want 10. We ask the model, we ask the sampling method to calculate the cumulative distribution, and in broad distribution, it will take more tokens and is narrow a small amount. So for example, here we have the examples of the broad distribution and narrow distribution, and how many tokens given that context we can take it into account, and in narrow not much, right? Okay. Now that we have talked about the possibilities of the model control, let's talk about the architectures. So the conditional music generation, which includes all three types of control that I presented earlier, have a spectra of architectures, of generative architecture that I used already, including vanilla versions of long-term shared memory networks, recurrent neural networks, transformers that have been mentioned already, variational autoencoders, generative adversarial networks, and even the reinforcement learning methods. But it also includes the hybrid methods, such as, hybrid versions of architecture, such as LSTM GAN or GAN with inception model, or conv-LSTM GAN, conv-LSTM, when we are giving the model the graphical input. Okay, now let's step back from the purely music perspective and try to see more like a global picture in what the current AI model exists. So with the great creative potential that AI model bring, we have a serious current print issues related to their training process. More accuracy means more parameters to take into account and huge data set use, which all translates to the power consumption and the carbon print. Another problem lies in the deployment and practical use of these giants that are trained on those huge data sets, which sometimes need to be hosted on a pod with multiple GPU nodes just for the inference phase. So we already trained the model, we already have the trained model. And in order to serve the predictions, we need to host it on multiple GPUs in a pod, because it's so big that it cannot be gathered into one GPU. Yeah, that's can create the latency issues and also consume a lot of energy, as you can imagine. So the alternative solution lies in the application of more neuromorphic approaches, such as spiking neural networks, that also called it the third generation of AI. So why the spiking neural network are so, what's the possible solution to this problem? Being coupled with the in-memory computing and event-based systems, spiking networks propose asynchronous processing, meaning that the spikes that neuron spikes asynchronously only to communicate information to each other, being in idle state the rest of the time. Whereas in current clock-based system, that we are using as of now, due to physical separation between memory and processing unit, not only the shuttling data between two consumes energy, but the values from non-informative neurons are also transmitted, created even more power consumption. Okay, so the bi-inspired neuromorphic sensors exploit the way the organic tissue processes the information via time-distributed spikes corresponding to visual, audio, or olfaction stimuli. Using the same paradigm of this asynchronous spikes processing, the neuromorphic computing chips are built. These computing platforms require the use of spike neural networks as the approach, allowing of the time-distributed data treatment. So, for example, here we see how the information processed by the retina of a mouse, but actually it's the retina of every biological being, I mean humans as well. So we are receiving the spikes of luminosity, and these spikes are time distributed. So more luminous points are going through faster, and then come less luminous. Here is, for example, the example of the audio input. So the audio, when it comes to our ear, right, it's actually has all of this spike representation, and then it's our brain that calculates the entire image out with these distributed spikes. So along with the environmental issues, the current music generation model have the aesthetic issues as well, which includes high diversity of music material in training data sets, which creates stylistic discrepancies of generated music examples. There are also difficulties of the internal latent space visualization that were pointed before. We have also the problem of the costly listening test due to low efficiency of the automated validation metrics. So one of the possible solution is a translation of the semantic information to a visual domain, which has so far gained more success in generation than music model, right, with the stable diffusion. This approach allows, so the translation of the semantic information into visual domain allows the application of the data augmentation techniques inherent to visual domain, the explainability of the internal space of the model via latent space visualization, and the application of the validation metrics inherent to a visual domain. Okay, so last year I proposed at EVA the new data content based of the system graphs. The system of graphs itself presents an analytical representation of functional correlation between chords, visuals at the degree of the diatonic scales, placed in a specific order, and the order is defined by the possibility of connection between the chords and expresses the variation potential within a multitude of chord progression. The procedure to receive the encoded representation lies in the replacement of the semantic chord designation by the numerical indexes that we choose with what we choose to represent the chords. So on the image here, we receive a 3x3 matrix, but if we repeat the described procedure, taking the dimensionality of the whole system, of the whole graph system, we receive the 28x28 matrix ready to be processed by a neural network. And here is the example of this encoded information. So here we have the designation of the chord that we are encoding using using this two-dimensional representation. Okay, the advantage of such encoding is the possibility of considerable data augmentation. Previously we talked about the discrepancies due to very diverse stylistic input, right? But with the data augmentation, we can take semantically same input, but augment it sufficiently enough for the neural network to be efficient in producing similar patterns. And so what we are doing, how do we achieve that? So we take a normal normalization term function, which is chord index divided by the vocabulary size. And we add the scalar, which is in range between 0.01 and 0.1. And in that way, we augment our initial manually crafted very little data set of 200 harmonic sequences into 2000 harmonic sequences using that approach. So the new data encoding scheme has been tested in an unsupervised setting using classical and spiking networks. The two data required implementation of an architecture capable to process sequences of frames. Therefore, a hybrid conv-LSTM architecture was chosen. In the conv-LSTM, each element of the sequence passes through the convolution layer and then followed by the LSTM layer. So here the experimental setup. I trained 10 shallow models. Shallow means that they are not deep. They were only 2 layers of LSTM. So the information that they are learning is is really shallow. So I trained 5 conv-LSTM models from the classical domain and 5 spiking conv-LSTMs. With the same parameters. So all the hyperparameters were exactly the same for these 2 kinds of models that are trained. And in order to do so, I used 3 data sets. So the moving MNIST data set, the original data set, which was proposed with the conv-LSTM architecture, a SegGraph, so our data set that we receive via the encoded technique that I just showed earlier, and the SecNIST. SecNIST was constructed by me manually. Why I did that? Because I wanted the diversity representation the same as in our SegGraph. Because if you see in moving data set, so this is the input, this is the target. So we ask the model to, given that input, please generate the target, please generate me the next frame. And as we can see in the moving MNIST, the digits are really moving. So what we do, we're not generating a new digit, we're generating the position, the new position of those digits. So it's more simple task than generate a distinct image. So in order actually to see how this encoding technique works with the neural networks, I needed to construct this SecMNIST, which contained the also the series of the distinct digits, in order to match the diversity of my dataset. And I also used the 2 data point set, so 200 data points. This compressed data set and 2000 data points. And in that, I used the moving MNIST that contained already that information and the augmented version of the SegGraph.
I'm sorry to say this, Anna, but you'll have to.
Yeah, moving faster. There is only 2 slides left, don't worry. There is only the generation that I'm using. So just to show you that with that little amount of data, the data set that matched the diversity of our data set didn't do well at all. I mean, it didn't really generated the target that we needed to have, while our data set actually had those distinguished shapes. And we see that spiking convolution neural network with the same parameter, with the same everything, has more distinct shape than the classical neural network. And it's even more obvious when we see when we work with the augmented data set, so augmented synthetically, as I showed you. So we have the ground truth and generated prediction. We can see that it's very distinct actually shapes. And with the classical conv-LSTM, we have too much noise to that. Okay, so wrapping up, in summary, it has been shown that the sparse nature of SegGraph data consistently gives better results in terms of the training efficiency, agreement of training and validation learning curves, and the clarity of generated images for spiking and classical models, with the best result received for spiking version of conv-LSTM trained on augmented version of SegGraph. The multimodal nature of constructed data allows further research on multimodal generation context, which is my current stage of research that explores generative abilities of spiking and ends in the context of music conditional generation. So thank you a lot for your attention. there is the reference, some of the reference that I've used during the presentation, and if you have questions, you are very welcome to ask.